Today I will talk about LLawCo, learning laws of cooperation. The motivation is simple. In embodied multi-agent tasks, LLM agents do not just need to solve the task, it also need to coordinate with another agent. But in practice, we often see behaviors that are misaligned with the partner or with the environmental state. For example, the agent may talk too much, repeat the same failed action, duplicate each other's exploration, or declare the task done before checking the actual state. So we ask a very simple question. Can we give the agent a small set of high-level behavior laws, like talk only when necessary or wait for the partner, and make the backbone LLM actually internalize these laws? Our goal is not to manually write a perfect rule system. Instead, we want the agent to learn the laws from its own interaction failures and then use them to learn to improve the cooperation. Here is the overall pipeline. We start with training episodes collected from the original LLM agent. Some episodes succeed and some fail. For the failed episode, we ask the backbone model to analyze why the task failed. These failure reasons are then summarized into a small set of behavior laws. For example, if many failures come from the repeated action or poor coordination, the model may induce laws like avoid infinite loops, plan before acting, or communicate clearly. Then we look at successful traces. We do not use all of them directly. We filter them by whether they are also aligned with the learned laws. From these retained traces, we regenerate the reasoning so that the thought explicitly refers to the relevant laws before choosing the action. Finally, we fine-tune backbone LLM on these law-guided thoughts and actions. So the key point is, the law is not only added to the prompt, they are also used to construct the training data so the model learns to reason and act in a law-aware way. At inference time, we put the learned laws back into the prompt, and the fine-tuned agent generates both law-grounded thoughts and the next action. To evaluate this, we introduce partner-dialog. The reason we need a new benchmark is that the existing communicative embodied benchmarks are either small or do not provide enough training data for learning-based methods. So we extend partner to explicit communication. We also optimize the evaluation system by decoupling the simulator, agents framework, and LLM server, so the large-scale evaluation becomes efficient. To better analyze what happens inside partner-dialog, we also build visualization tools. The original partner visualization mainly provides a third-person view with action annotations. We extend it with a top-down view, so it becomes easier to inspect spatial coordination between agents. We also explicitly visualize talk actions. Since communication only lasts for one step, we pause the visualization briefly when a talk action happens, so the message and the surrounding context are easier to read. Here are the main results. The right table is partner-dialog. Across different backbone LLMs, LLawCo consistently improves over communicative baselines such as LLawCo, Qoella, and CompPartner. One important point is that the improvement comes from self-alignment of the same backbone model, not from a stronger model supervision or extra external data. The left table is on TDW-MAT. We see the same trend here. LLawCo improves performance across model families and object categories. And Qinhong 14 billion with laws can outperform baselines built on much larger language models. So the takeaway is not just the laws help on one benchmark, they improve cooperative behavior across different environments and different LLM backbones. Here are the examples of the learned laws. They are compact and interpretable. For example, plan before acting, use clear and effective communication, avoid infinite loops, and confirm completion. Across different backbones, the exact wording changes, but the themes are stable. Coordinate with the partner, communicate only when useful, recover from failures, and verify completion. So the laws gives us a readable interface to inspect and potentially edit the agent's behavior. The upper ablation shows that prompting is not enough. removing SFT, loss, or log-added filtering alters performance. So LLawCo needs both the learned loss and the fine-tuning step. The lower intervention shows controllability. Under the same state, replacing the loss changes the model behavior largely. Here is one TDW-MAT example. At the beginning, Alice begin with a plan and propose the division of labor. Bob then follows minimize redundancy, so he explores a different room instead of duplicating with Alice. Later, Alice finds objects and a container and follows prioritized containers to pick up the container first. This shows that the laws are not just texting prompts, they guide communication, planning, and task execution in a visible way. This example shows that the log-guided planning on the Qin 3 14 billion PARTNR-Dialog benchmark. At the beginning, the robot follows the law plan before acting. Instead of immediately committing to an object or room, it first explores the relevant area to get the information. And later, the human partner follows the use clear and effective communication law and sends a concrete instruction, asking the robot to place a candle on the coffee table. So the main point is that the laws encourage use for early planning and precise communication. And the second example is on JAMA 3 12 billion, and the loss here looks a bit different. For this backbone, many failures come from execution level issues, such as invalid action arguments or missing prerequisites. So the induced loss emphasize things like validate action syntax and constraints and manage dependencies and prerequisite actions. In this case study, before placing the toy food on the counter, the agent explicitly checks whether the place action is valid. Near the end, before calling down, it checks that the task dependencies have actually been satisfied. This shows an important property of LLawCo. The laws are backbone aware. Different models have different weaknesses, and induced laws reflect the kinds of failures that each model tends to make.